Αγιομέτρητος μεδέης εισίτο.
Why am I telling you about do calculus? So I want to convince you today that it is a truly unique technique when it comes to studying causality. And it's particularly relevant for us as neuroscientists. It's an important point I want to make today. And one of the reasons is that the other techniques that we have and are familiar with, they're fundamentally pairwise. That's not necessarily a problem of these techniques. It's a problem of most of mathematics. So whenever we deal with numbers, baked in the cake of a definition of number is pairwise operations, addition, multiplication, division, you name it. But of course, in the nervous system, and I will make this point repeatedly, there are non-pairwise effects. We call them higher order effects. And people are aware of that, and they try to do this in the following way. They look at combined effects by breaking everything down in pairwise effects and then reestablishing the higher order. So if I say, what is 2 times 2 times 2? You say, I can immediately multiply these three numbers together. But what you actually might be doing is you calculate 2 times 2, and then you multiply it by 2 again. So as long as you're dealing with systems where you can combine things such linearly, you're fine. But I will argue that is not the case in the brain. And lastly, and this is maybe the most important part, what do calculus does, it really gets at causality. This sounds like a big claim, but just bear with me. Whereas the other techniques that we have, and so I'm pointing out Granger causality and I'm putting causality in scare quotes, is that they are talking about predictability. And as I will make the case, predictability is not the same as causality. In particular, and this is just to maybe raise your interest, if you ask ChatGPT what the problems are, for example, with Granger causality, then the first thing that pops up is what we call a confounder. So in neuroscientific terms, this would be if we have two neurons and they both get inputs from a third neuron, and you don't know that, then your analysis might give you the erroneous result that both of these neurons do something causally, but they might not even talk to each other. It's the common input, the common driver that is causing that. The do calculus can be robust against that. So in do calculus, even unobserved confounders can be found. And again, I don't have to probably make the case here why that is important in neuroscience. Now, there is an asterisk. There are a lot of course, as always, in mathematics, all of these techniques, assumptions that go into that we have to make sure we're not violating. And so I will talk about these potential pitfalls as well. But let me come back to this higher order effect. So it's actually really difficult to think of things in the real world that are not fundamentally pairwise. The one thing that I keep coming back to is fire. So in order to get combustion, we need oxygen, we need heat, and we need fuel. And they need to come together at the exact precise same time. And any combination of those two, if you just use oxygen and heat, or just fuel and heat, any of these combinations of the two, if you're studying them in isolation, you would never know that if you put these things together at the same time, you get fire. None of these give you fire. So if you're trying to understand this ternary interaction between these three things, by studying the system, by breaking it into pairs, you will never know that if these three things come together, you get a different effect. And this is true for the brain. So this is a Nature paper by Madi Asri, Jose Manuel Alonso, and Reid. This is actual data, but I'm trying to make it cartoonish here just to simplify what they've been doing. So they were recording LGN neurons and V1 neurons, and they got lucky enough, or they worked hard enough, I should rather say, to find two LGN neurons, and I'm labeling them here as A and B, that converged onto the same V1 neuron. So they had two inputs and one receiver. So the V1 neuron would be neuron C. And they did a very simple analysis. This was in 1996, I might remind you. So what they found is that when neuron A and the LGN was active, there was an enhanced likelihood, probability, that the V1 neuron would become active. It's not huge. It's relatively low, but we would expect that if that's just one of the synapses that might get innervated. Likewise, they could compute whenever the other LGN neuron that recorded at the same time was active. They also found that the V1 neuron had a slightly enhanced likelihood of firing 8 milliseconds later with the synaptic delay. But what they found, and why this was published in Nature, was that if both these LGN neurons were simultaneously active, the likelihood of that V1 neuron firing jumped up not by the sum, not by the product, by way more than, again, what you would have expected if you would have studied the system in isolation. And so this is only one example. And so interestingly enough, when I presented this years ago, some people would question me and say, well, maybe they found the one example in the brain where that happens. But in the paper, actually, they list 16 more of those examples. So in fact, most of the neuronal triangles they recorded had that effect. And it shouldn't surprise nobody. This is what Donald Hebb said that happens. That's what we call a Hebbian synapse. But it's a ternary interaction that can't be understood by pairwise interactions. Okay, so the reason that I'm pointing this out, I think this is actually underappreciated because there's so much talk about computational neuroscience, and this is not a computation. Why? Because if we look at when I ask people what's a computation, they say that's what a computer does, right? So you can actually summarize that it's saying it is a Turing machine. There's all of these different definitions. You can also say that it operates on Booleans. And so that would be, if you even want to simplify it more, lambda calculus. Lambda calculus explains computations because they explain what a computer can do. But if we zoom in what a CPU does, of course, what we find are logic gates. And if we look at individual logic gates and XOR and so on, they perform, yes, Boolean logic, binary logic. But what they do is, of course, they have a transistor that flips. And for a transistor, the physics, it doesn't matter whether the inputs come in simultaneously, yes or no. So the brain seems to do something here that your computers can't do. So either we broaden our definition of computation, or we have to drop that notion that these Boolean operations that your computer does is what your brain is doing. So that's why I'm thinking that's an important point. But because we neglected that by breaking everything down into pairs, we might have missed this very important point. It might also explain why your computer is getting hot as it sits right there and your brain isn't. Your brain uses about 15 watts, which is about the light in a refrigerator. ChatGPT 3, that's the only AI for which we have data, used several gigawatts, so more than one nuclear power plant to get trained. Okay, so do calculus, as I said, to repeat that, it can detect and discover causal connections. It can quantify these causal connections. That's another important thing I will talk about in a moment. What do you mean by quantifying causality? And it can do all of this for these things, a non-pairwise higher order, and there's no limit. It doesn't have to be 3 things interacting. It can be 6, it can be 1 billion. Okay, but in order to do that, so how did Judea Pearl get this? All of this might sound fantastical to you. And in fact, most of the work that Judea Pearl did was to convince people that his logic is sound. And what he did was different to what we're used to in statistics, is he asked this question. And so I repeat, what is causation? What do we mean by that? And so he showed that in the beginning of statistics, people were inspired by Russell, and they didn't believe in causation. So there are quotes where they said, all we can do is observe correlations, and we should stick to that. And so that is metaphysically true. All that you can observe are correlations, if you think about it. Even if you think that you're causally manipulating something, you're doing action A, and then action B happens. Might be a perfect correlation, but it's just a correlation. Nobody has ever seen a causation. They are an assumption that we put onto the world. All that we observe, that is Russell's argument, is things to correlate. And people took this very seriously. And until Judea Pearl, that meant that scientists were trained, including you, including me, to stay away from the term causation because it is metaphysical. And so it's not metaphysical if we can formalize it and do math with it. So correlations don't really tell us what one thing causes another. That is obvious. So in summertime, more ice cream gets sold and more drownings happen. That doesn't mean that because drownings and ice cream correlate that people drown on ice cream. Trivial, right? So causation is something different. Now, what Granger causality is trying to do, and other techniques, is they're correlating and they're shifting in time. Now, that's a benefit. That's better to say that I know that one thing happens before another. That's what we call causality, but it's still associative, correlative. It's still saying when this happens, something else happens. And as I showed right at the get-go, that can lead to erroneous results. So what Judea Pearl said is, it bothered him that scientists use equations in the office and then talk cause-effect in the cafeteria. He would go so far to say that physicists talk, write, and think one way and formulate physics in another. And so what he pointed out, if you really go to the foundations of science, we all probably are reductionists, and we believe that we are studying biological systems. They're reducible to chemistry. Chemistry ultimately is just physics. And what is physics? F equals m, A, E equals mc squared. You have equations. Now, an equation has a problem. That's what he meant by they write equations and talk cause effect, because in an equation, there is no cause. E is mc squared. There is no time in there. Energy and the mass times the speed of light or the speed of causality squared is the same. It's a state. It's instantaneous. F equals ma. The force is the mass times the acceleration. There is no delay. So how can you go from these equations to causation? And so what he realizes, there's a problem in notation. There's a problem in using the right symbols. An equation is literally, if you look at the symbol of an equation, it means you can go left to right and right to left. A is B, B is A. And that doesn't lead to causation. And he's not the only very smart people who thought about it. So there's another hero of mine, Michael Nielsen. And so he wrote this whole blog about if correlation doesn't apply causation, then what does? Spoiler alert, he says it's do calculus. So let's work through that. So what did Judea Pearl find out by rethinking what causation really is, or what we intuit what causation is? So we have to rethink what we mean causation is. So the first interesting thing that he found out is what we call partial determinism. So that perplexed the physicists around 100 years ago. So when they discovered quantum physics, they learned that if I have Schrödinger's cat in a box, we assume that ontologically, truly, really, physically, the cat is dead and alive at the same time. Now, we can't catch it in the act, because for some quirk of nature, the moment we look, the quantum superposition collapses and we only get a determinate outcome. Half of the time it's dead, half of the time it's alive. So there's a causation between the state of the cat being dead and alive and what I find. But there is the stochasticity in there. So it seems to cause it to be dead half of the time and alive the other half of the time. And so if you look into the writings of Niels Bohr, he thought initially that means there is no more causality. They ended up back saying quantum physics robs out us of causality. And you might be smirking because you understand, well, causality can be 50-50, it can be causal. So typically when we think of causality, we think of fully determined. So what we mean is 100% likelihood. So one thing always occurs if another thing happens. So each time I drop a heavy object, it will always fall to the floor. It's fully determined, and that is what we usually understand as causation. But if you ask people, does smoking cause cancer? They say, yeah, but it doesn't all of the time. So when we look at the likelihood of smoking causing cancer, it's about 25%. Yet people still think that's causal. That is what we call partial determinism. So it's not fully causal, it's not fully deterministic, 100%, it's 25%, but that's enough, all right? Now, the next thing that Judea Pearl talks about, I also find counterintuitive at first, which is that causality is not about doing. That is actually a very common and very modern confusion. People tend to confuse being with doing. So they define what is by what is being done. And so again, in computational neuroscience, that is very common to just focus on the action. And when it comes to causation, it turns out the action alone, the output, the outcome is not enough. So in other words, when we say, well, look, the AI does what we do, the outcome is the same. And then people argue whether the AI is intelligent or whether the AI is actually thinking, or let alone if the AI is conscious. Well, you're just focusing on the output. And so let me give you a very clear example. So let's say you drive home and somebody crashes into your car. Well, in one case, you learn that that person had a stroke, and in the other case, you learn that the person was on their phone. Would that matter to you? Who would you be more mad of? This example, I think, shows that if we only look at outcome, we're missing something about causation. Real causation is more than a prediction where we're interested in what happens. And I don't care how it comes about. I'm only interested in what happened. Somebody crashed my car. But our intuition tells us that the how is actually part of the story. So, and this is very important to what I will say next. If we want to understand causation, including formally mathematically, the how is extra information that pulls the data from associative correlation into causation. Now, the last one I think is maybe the most interesting one. And so it's called inactive causation. And so it goes hand in hand with what I just said. There's this overly focus on action, on doing things. And in the brain science as well, what are the neurons doing? What are the computations? But not doing something is actually almost often as powerful and sometimes even more powerful. So when a neuron does nothing, we think that neuron has no causal effect. It does nothing. I can ignore the neuron. And I want to convince you that can be as powerful as if the neuron is active. So this is inactive causation. So here's the example. So somebody does something really effortful to impress you, and you say something. Let's say you say, thank you, or that was great. So now the person is happy, everybody around you is happy. There was the social expectation that if somebody does something really nice for you, you say thank you. So that's action-based causation. We all understand it. But let's imagine you say nothing. So somebody does something really impressive, really nice. They gift you something outrageously, and you just stand there and make a face. No, thank you, nothing. Well, in this case, everyone around you gets the feeling of this is awkward. The other person might become very unhappy, sad. So even though you did nothing, you caused something tremendously. So inaction also has a causative effect. So how can we formalize that? How do we get that causally? So what I'm saying is that it's not only important when we think about causation, what actually happened, it's also important to consider what could have happened or should have happened and didn't happen. So while most causation is focusing on the factual, what did happen? What are my observations? I'm claiming with Judea Pearl to really understand the full picture of causation, you also have to understand the counterfactual. The counterfactual are the alternative worlds where this could have happened. In this world, it didn't happen. In another world, it did. So I could have said thank you. I didn't say thank you. So because I didn't say thank you, that's saying thank you, the counterfactual, the thing that could have happened and didn't happen. And so Judea Pearl puts this together by saying that there's a ladder of causation. If we're trying to understand causation, things go from poor, which is just a correlation, which seems like a prerequisite for causation, but it still doesn't give us enough, to the next step where we understand a little more. So of course, if we do regressions, correlations, all of these techniques, we're just, again, Granger causality, we're staying in correlative approaches. Now, the way out that we teach students is usually you have to do a causal experiment. And what is that? You have to do an intervention. You have to go in and change something and see what happens. And Judea Pearl says, yes, I agree, that's better. So that is the next rung on the ladder. It's better if you do an intervention, you do something, and then you see what happens. Agreed. And so, of course, that is a superior technique. But what Judea Pearl, given everything that I just said, what he says, it's not enough. So even if I do experiments and I intervene in the brain, I still don't get the full picture. So I only get the full picture if I also factor in the counterfactuals. So I do not just have to study what happens if something gets done. I also have to take into account what could have happened and didn't happen. And so that is what I will show you next, where do calculus comes in. Judea Pearl says correlations, they tell us what happens. And with an intervention, I get added information why something happens. It's because I did something. But really only if I factor in the counterfactuals, I learn not only what happens, why it happens, but also what would have happened otherwise. And so that is what we need for causation. So the long upshot here is that we need to observe correlations. That's still our starting point, because that's all we get. That's how I started out. Everything that you observe, everything that you measure is correlation in the real world. Now, we want to intervene, and there I have the good news. That doesn't mean you have to do an experiment. That doesn't mean you have to physically intervene. We can intervene mathematically. That's where it gets really interesting. And then lastly, and that comes with these mathematical interventions, we want to study all of the counterfactuals. And if we do all of this, then we're finally done. Okay, so we rethought causation, and so now we end up with what we call Pearl causation, or do calculus, also called model-based causation. There's all of these other names. So where are we getting there? So the first step that I think was important is to develop formalism. Why is this important? Everything that I told you so far was just words, just concepts. Woolly words that some people might understand differently from me, and so most of the debates that we have is because we're using language and it's flawed. Formalism doesn't do that. The reason that mathematics, one of the reasons why mathematics is so powerful, is that it uses notation. Formalism, if I have an equation, is consistent and reliable. Consistent, it always gives me the same result. Reliable, anybody can try it. And so what that does, it eliminates both inconsistency that we have in language, and inconsistency gives rise to confusion. It also, the reliability eliminates uncertainty. So once we have formalism, we get rid of confusion, we get rid of uncertainty. That is why I'm a big champion of formalism, and Judea Pearl was as well. So what he realizes, the formalism, as I said, that we have with an equal sign is flawed, because there is no sense of time. And the one thing that we think about causation is it's asymmetric in time. It moves one way and one way only. And what he realized, looking into how people have solved it, is people have solved it. You have all solved it, which is that when you ask people what is causing what, they do this. They show you a bunch of arrows. Yeah, so indeed, an arrow is a better notation. An arrow goes left to right, implicating present to future, or past to present. So instead of an equal sign, we want to have an arrow. Okay, so now you introduce some kind of new notation. Well, the thing is, you're all familiar. Arrows give us directed graphs. This right here is a graph, and we have already the mathematics. So a directed graph, where we think this is the flow of causation in your system, is all it takes to move out of correlation. So I said we need additional information to take your correlational data and turn it into causal data. That's it. You need both. You need your observational data, and then you need what Judea Pearl calls a structural causal model. Structural because it has that structure of these arrows, and it's a causal model because we're saying the notation of an arrow stands for this causes that. And again, keep in mind that this arrow can also be different thickness, can be a weighted graph where I can denotate different strength, causality. So while this right here is primitive and people have done it right out of intuition, they didn't realize, oh, that's a graph and I'm studying causal systems here. They just try to convey their message visually. What we don't have here is that this is not derived by algebra. Right here, there is no correlational data that's part of it, and there's also no causal quantification. So how do we get that? So I want to basically answer this question again. If correlation doesn't imply causation, then what does? And I'm saying it's additional information. It's the SCM, the structural causal model, or the graph. So when I said we have to do all of this, we can do this with an SCM or structural causal model. So once we have a structural causal model, what we can do is we can both intervene, and I will show you in a moment how, and we can compute all counterfactuals. Now, I told you that if this almost sounds too good to be true, that's because, as all techniques, we're making assumptions, and you can't violate the assumptions. And so the crucial one is that because I'm saying so much relies on the structural causal model, if you get that wrong, then you might get also the output wrong. Now, there's some good news, and I indicated that before, that what do calculus allows you to do is if your data is perfect, then you do not need to know the structural causal model. You can then infer the structural causal model from your data. Now, if you have a perfect structural causal model, then it doesn't matter so much if your data is noisy. We might, most of the time, have an intermediate point, and so I will today make the case for trying to get as much data as we can because we're data rich. And so once we have enough data, then maybe we can even do with an imperfect structural causal model or just go in ignorant and let the math work out the structural causal model. Now, the important thing, and I almost glossed over that, is that do calculus does not prove causation. So there's nothing in the mathematics that shows this is causal. Why? Because the causation is axiomatic. We started out by saying that if there is an arrow in my structural causal model, that is what I call causation. Now, because it's a graph, we can establish these arrows, but it doesn't take away the fact that we axiomatically define an arrow, that notation, to be causal. So we can find arrows, and then we say that's causation. That's why it was important for me to build up that intuition that you agree with me that what this arrow denotates is what you also intuitively feel is causation. So if you're on board, then you can do that. So again, if you have perfect data or you have a perfect structure causal model, so if with 2F means if and only if, the causal model is correct, then all of this is valid. Okay, so how do we do as neuroscientists on this? In neuroscience, we actually have a big benefit. So what is it? So I think what we have in neuroscience is that we need to have the structural causal model, and we already have that. That is what we call connectivity. We know that if a neuron is in the front of the brain and has no connection to the back of the brain, it can causally affect the back of the brain, not directly so. Your structural causal model, the graphs that we use in neuroscience, is usually what we call a connectome. May be anatomical, functional, effective, but that is a structural causal model. So you might already have everything that you need. We have the connectivity often, and so what that means, let's assume that we have perfect connectivity. Let's assume it's perfect. Let's assume that anatomical connectivity would be the last word. All of that is questionable, but assume that's the case. I think this is very important. So if we would have a perfect structural causal model of what can cause what in your nervous system, then what I'm saying, that's a one-to-one model, and that's very important. A one-to-one model means you have a digital twin. Why is this important? Not all models are wrong. A one-to-one model is 100% correct by definition. It's a copy. It's the real thing. It's like saying, what's a one-to-one model of the Isle of England? It's the Isle of England. But if you would build it on a new planet, quantum by quantum, it would be a one-to-one model. It would be the real thing. It's a copy. It's not wrong. It's perfectly correct. We're only interested in one model, which is what is the causal flow? I don't care whether that neuron is brown or black, or white or yellow or green. It doesn't matter. Of course, there's additional stuff in the real world, but for the causation, it makes no difference, right? So I need a one-to-one model of just the causation. That's it. And if that's perfect, I can perfectly describe causation. Okay, so let's say that's the case. Now, if that's the case, if let's say we have a perfect one-to-one model, that means now we have a digital twin and we can experiment in silico. That is what I was getting at before. You can do interventions without going back to your laboratory because you have a one-to-one model right there about what you care about, is what is causing what. Again, it doesn't matter what the particular details of the neuron are, you have what it takes. And so that is what Judea Pearl came up with. And he said, what are interventions? And this is, as you will see, the whole magic. An intervention is changing values within your digital twin. That's like going in and changing things. That is what we'll call do. What you do is you intervene. And the outcome, the change that evokes in your system that you compute, is what we call causal power. It's just the difference, the before and after I do an intervention. Now we'll show you how this is done in a moment. Judea Pearl called these interventions surgeries on equations because you can actually take any graph and retranslate that into equations. And what you do is you're guided by the diagram. You're guided by the structural model of all of these arrows. And then you quantify these surgeries, and that gives you a scalar of causation. So I want to go over that, again, without going too deeply into the equations, just give you a feel for that and show you how this works in neuroscience and why it works so well for neuroscience. In fact, if you look at the graphs that Judea Pearl came up with, they look like neuroscience. So he would say, this right here is my causal model. And so that's a structural causal model. So what I can do now, because I have this in silico model, I can intervene. Remember, what I do is I just change something in my model and calculate the difference. And so what he says, why he calls it surgery, is I can mutilate the graph. So what I can do is I cut right here this arrow so that this has no more effect on my data. So by mutilating that graph, I've intervened. So that is what he came up with new notation for that. That is why it's called do calculus. So this operation of mutilating the graph is what he calls do. It's a do operator. And he just sets this variable, let's say that's the variable x, he sets it to a discrete value, let's say 0. And you do that, again, computationally. You don't have to do it in the real world. So do just means setting to a fixed value. So you have these different variables. There might be different neurons, different electrode contacts, and you're fixing it to a value, and you see what happens. So how do you do that in our data? So if I have different neurons, do that by setting it to a fixed value. So I collected my data. I get the data from the Allen Institute or from Chant or somebody else. I can't go back and do optogenetics and inhibit the neuron. But I want to know what happens if this neuron is not doing anything. Well, the answer is we already know. Because, of course, a lot of time in your data, this neuron is inactive. That's the same thing as inhibiting it, if you think about it. If there's any downstream effect of this neuron being silent, it doesn't matter whether you go in and do this with optogenetics or whether the neuron is silent. So what you'll have to do is you basically go into your data, you find where the neuron is 0, and then you average the data. So we call a spike-triggered average here would be a non-spike-triggered average. But of course, you can do the same. When the neuron is active, it's set to 1. You do a spike-triggered average. So at this point, it still seems trivial, and this is not entirely the magic yet, but it's already getting us to this point. So a spike-triggered average, you can think of it, if you have a good causal model, that it already would give you an idea of causation. So in this very primitive sense, and you will see it in the exercise we'll do in a moment, do calculus, if you do it in this very loose way, and I would call it loose, it actually just boils down to conditional probability, right? So it's a conditional probability where I look at the rest of my data given my neuron is 0 or given my neuron is 1. And as I will show you in the exercise, of course, that still suffers. That's basically a regression. But you tell me all of this and you're doing a regression? No, we can go further. But that's a first step. So what's the first problem? Well, the first problem is I'm not just recording one neuron and another neuron. That's pairwise again. I'm having 400 neurons. So what I'm telling you is yes. So when that neuron is inactive, you want to see what all other 399 neurons are doing. So you have to do it for all of them, and you have to do it when the neuron is active and inactive. If you have 2 neurons, you can see you will quickly run into quite a bit of combinatorial explosion. So if I have neuron A and B, what I really need to know if I want to see, are they connected? Are they doing something to themselves? Is there a loop back to the neuron? What I have to do is I have to look, let's say A is inactive, then I have to see what happens next. Is A inactive and B inactive? Is A still inactive if B is active? Or maybe both of them are active now. Or maybe only A is active and B is active. all of these, because we're looking at counterfactuals, I want to see everything that could happen and what might happen. So I have to do this. And of course, then I have to repeat it because I have both neurons. I have to do this where B is inactive. I have to do when A and B are inactive. So you can see basically I get an M by N combinatorical possibility space that I have to fill out to really get all of the answers. And then I'm done. So the problem, though, if you have been thinking along, might be, well, but in the end, I want to have one number. How causal is it? Or one arrow. But you're telling me I'm making a lot of comparisons. If this happens, then this, and then this, and then it. So how do I deal with it? And so that is a little bit of a problem. So in the simplest case that I said, you end up with 2D distributions of probability. So I had a certain set of probabilities, and then I see what happens at the next step. And so what I really have to do then, if I look at, so what's the probability of A0 and B0 or A1 and so on if A was inactive or A was active? Well, I have 1, 2, 3, 4 numbers for this one do operation. So what I have to do is very simple. Instead of saying, well, I have not one number, I have 4 numbers. I have a vector, and I want to compare the vectors. And so that is what we do. So if the outcome is more complex, all we have to do is now we have 4 numbers, so it's a vector. So then you can choose your favorite vector comparison technique to find the difference or the distance between the vectors, and that is the answer. That is what your causation is. It's the ultimate difference. And again, remember, it's not just looking what A0 is doing to AB, but also to itself. And whether it is causing B to be active or inactive, it's the whole counterfactual space that makes us so powerful. So how do I do these comparisons? And so again, there's a myriad of ways to do it. You're going to end up with something like this, where you have something before and after intervention. So I'm taking this from the excellent tutorial by Will Mayner, Billy Marshall, Larissa Albantakis, Graham Findlay, Robert Marshman, and Giulio Tononi, where they walk you through this logic. And so what they're slowly introducing in these papers, so what they're showing right here would be neuron A being inactive, would be an empty circle, B being inactive, another empty circle, neuron A being active is a filled circle, or inactive here, or B, and so all of the possible states of these neurons, and then you see how often does this occur. And then what you do is and I haven't shown you how to do this yet, the graph mutilation, the intervention, and let's say you find this distribution. And so you don't have to worry about the details, what I'm going to show you next, but a lot of you are probably familiar with that. It's used in machine learning AI all the time. You want to know what's the difference between, or you want to quantify that. And one way to do it, an easy way, is that you just move things around until this looks like that. And so this would be what's called the Wasserstein distance or Wasserstein difference, if you want to pronounce it English. It's also called the Earth movers distance, because you can think of these as earth hills that are being moved by a caterpillar. But the important thing is that it gives you a measure, right? So you get these two distributions, and you can say how far apart are they. There's different techniques, Kullback-Leiter, KL distance. There's other techniques that are more popular. They all will work. They will give you, of course, different numbers, different units. But I'm just saying it's easy if you want to compare two things that are not just single numbers, if you have a vector of multiple numbers. OK, so how does this work in practice? So what we really want to do is, let's say you have a bunch of neurons and you're recording them. So you want to do exactly what I said for these all of these data. And that's because you want to catch also that if 2 neurons are active and they are connected to a third neuron, that this happens. And so now you see that, again, I'm not relying on the data, because what I will do is I will remove these arrows, I will remove these graphs, and then my model, I will also introduce what I will call a hyper arrow. So this is an arrow that connects, it's an edge in a graph, but it connects 3 nodes. So regular edge is a line or an arrow, right? So it always connects 2 nodes. That's what we call a bigraph, because it's 2 things being connected. This is a hypergraph where we're connecting 3 things at the same time. You can think of these as lines, 1-dimensional, and this is a surface. It's 2-dimensional. And so the model that I'm telling you is it can do surfaces, it can do 3-dimensional structures. So actually what we're going to move into is a topological space. This is where it gets really interesting. OK, so this is another paper by the same group. And so what they're doing is they're saying, let's say, keep it simple. We have 2 neurons. And so to, again, keep it simple, let's assume that they both follow Boolean logic. That's an OR operator, and that's an AND operator. And what they do is they can bidirectionally exchange signals, and they also impact themselves. Now, I want to briefly talk about that. So one thing that I see in the data analyses that people do when they look at connectivity is that they're sticking to bigraphs. So they're usually looking at pairwise connectivity. And the fact that 2 neurons, when they're active at the same time, that gives you a different result is often put under the table. But so is this. It's very difficult, if you look at your data, to find out if a neuron actually impacts itself. But we do know that axonal branches can impact a neuron itself. And so these feedback loops that are acting on the very same neuron, they often also fall out of these models that start out with this assumption that each node is a neuron, and the only thing that I allow is linear connections between pairs of neurons. So this is going to be important that these neurons impact themselves. So here's the actual formalism. So what we do is now we're treating the system as a Markov chain. So remember, a Markov chain is that we have states and then transitions between states. And the idea is that if we have a full statistical description, that's all we need to know. Remember what I said about the one-to-one model? So the simplest Markov chain is today is sunny. What's the likelihood that it will rain tomorrow? Let's say it's 50%. Well, today is sunny. What's the likelihood that it will be sunny tomorrow? Let's say it's 50%. But you can put in other numbers. So let's say today would be rainy. What's the likelihood it's tomorrow sunny or rainy? Let's say it's either 50%. Well, that's all you need to know to describe the weather into perpetuity. Because every day it's either rainy or sunny, and you know the probabilities that the next day will be rainy or sunny. That's why it's called a Markov chain. It's a chain of states. And if I know all the states that can occur and the transition probabilities between them, I have a complete description of the system. There's nothing else that I need to predict the weather the next day with that precision. Okay, so we're doing this for the brain. So what we want is a transition probability matrix where on the columns, we start out by writing all of the possible states that could occur. That's why there's a combinatorial explosion. So for two neurons, as I said, both can be off, one of them can be on, and so on. So let's say both of them are off. And so what I'm interested in is, again, the facts and the counterfactual. So I need to know everything that could happen. So what could happen? Well, there's 4 possible states. Both neurons are off, both are on, or one of them is off and the other one is off, or vice versa. So what I have is now a row where I have these neurons are off, and these are all possible future states. I'm denoting as t+1. You can choose the time step, whatever you want. So we're looking at a present state, at a state in the future of our choosing. And so now what we need to do is just fill in these probabilities. What are the probabilities to transition out of this state? Let's say it's a deterministic system. So it's an OR and an AND gate. There's no noise. So what you find is if both of them are off, then both of them will be off with 100% probability, likelihood of 1, that will both be off in the next state. And these states don't occur. Okay, so now I have to do this for all the other states. So let's say this one is on and this one is off. What I find is this and so on. So I can fill out this table. And again, these are zeros and ones because it's a fully deterministic system. If we have partial determinants, this could be 0.5, this could be 0.25, and so on. Then what you really want to do, this right here is not a structural causal model. So this is actually our physical reality. The structural causal model is a graph. More specifically, it's a directed acyclic graph. So this would be the structural causal model, where I have the OR and the N at the present and the future. And so now I have to encode with these arrows all possible causal interactions. I don't know whether they occur, but let's just saturate this model and say everything could occur. Let's test what does or doesn't occur. So OR could influence itself. This is this arrow. OR could also influence AND. This is this arrow. AND could influence itself. This is this arrow. Or AND could influence OR this way. So this right here is our SCM, our structural causal model. So what we have now is a structural causal model and then the correlative observational data. That's all we need. Now, how do we do the do calculus? This is where we move away from this very strict thinking about conditional probabilities. Because since this describes our system so well, we can now do the operation on this table. So remember, the idea is, and so for our neural data, we can make sure that this table, if we add more and more data, it doesn't change much anymore to certain floating point precision. So we have trust that this transition probability model, it explains very well our data. That Markov chain, it really describes the statistics of our data. So then we can ask the following. So for example, I want to do this do operation where I want to make sure that one of these neurons has no causal impact. So I'm wondering, is the structural causal model correct? Where I'm assuming that it can influence itself, it can influence the other neurons. So how do I find out? I find out by cutting it out of that causal system and seeing what happens. If nothing happens to your whole data, then that neuron had no effect. That's why it's not prediction. This is real causation. We're cutting it out of the model. I don't see an effect. Now I know, lo and behold, it had no causal effect in my data. So how do we do this mathematically? Well, it's very simple. So if it doesn't do anything, we just have to find where it doesn't do anything. And then basically, we just have to average that. So what we do, and so it's basically, if you want to be technical, it's statistical marginalization. So we find where this neuron is inactive, where it's inactive, and then we average this. And then we, of course, have to see what happens then for these states. So we average, in this case, the rows. So in the end, what we find, because we're averaging these values, is now we're getting a new transition probability matrix that's basically showing us our data without that neuron. So now we're left, this neuron is grayed out. We marginalize it out. We just averaged all of these lines together as if it wouldn't exist. And what we're left over is just the data where that neuron that we still have in our model, where it is doing something, and then we're looking at that effect. So that right here is the mathematical equivalent of that right there. And so then all we have to do is compare the difference between these transition probability matrices. And that gives us an indication that there was a causal effect. Now, if this would have not been causal, then this mutilated, intervened transition probability matrix would have looked exactly like this one. And so you will see in your data that happens very often. So you cut something out of your data, a neuron out of your data, and it doesn't change anything. And that's how you know that neuron never had a causal effect in the first place. Okay, so then let's do it in real data. I have two data prepared for you. One is synthetic data, so we know the ground truth. We're going to model some neurons. We know the connectivity. We see what it does. More particularly, and I will show the code in a moment. We have a computation model of 3 neurons. They have Poisson distributed baseline activity, are spontaneously active. And our task is to find the causal connections. Now, we do know them, of course. We know the ground truth. We want to see how well this does. And then we do what I just told you, and then we do Granger causality, transfer entropy. We see how all of this does. Now, if you're unsatisfied with that, we will look at actual neural data.